Have you ever wondered where it all began, where we came from, and what's the origin of this vast universe? These questions have intrigued philosophers, scholars, and scientists alike for centuries, pushing the boundaries of human curiosity and intellect. The universe, a complex and intricate tapestry of matter and energy, is a grand cosmic ballet. Its vast expanse, studded with galaxies, stars, and planets, is the stage upon which the drama of existence unfolds. But what is the prologue to this grand narrative? What are the opening lines to the story of everything? Throughout history, humanity has proposed various theories and beliefs to explain the origin of the universe. From ancient cosmologies that saw the cosmos as an eternal, unchanging entity to modern theories that envision a dynamic, evolving universe, our understanding of the universe's inception has transformed dramatically. Ancient cultures, from the Egyptians to the Mayans, have offered their own interpretations, often entwining cosmic creation with divine intervention. The Greeks, for instance, proposed a universe born from chaos, a primordial state of emptiness. In contrast, Indian cosmology describes a cyclic universe, one that undergoes endless cycles of creation, preservation, and destruction. In the realm of modern science, several theories have been proposed, each shedding light on different aspects of the universe's birth. The steady-state theory, for instance, suggests an eternal, unchanging universe. In contrast, the oscillating universe theory posits a universe in a constant cycle of expansion and contraction. However, the most widely accepted explanation today is the Big Bang theory. This revolutionary concept takes us back almost 14 billion years to a singular point of infinite density and temperature. It suggests a universe born not from the whims of deities, but from a colossal explosion of energy and matter, setting the stage for the cosmic drama that continues to unfold. The most widely accepted explanation today is the Big Bang theory, a concept that takes us back almost 14 billion years. Picture a time when there was nothing, an absolute void, and then suddenly a singularity appeared. Imagine a point so infinitesimally small, yet containing such massive density that it's almost impossible to comprehend. This, my friends, is the concept of the singularity, an entity of infinite density and unimaginable heat. This singularity, which seemed to have appeared out of nowhere, was not just an ordinary point in space. Rather, it was the entire universe, compressed into a tiny, heated mass. The singularity was the epitome of everything we know and everything we don't know, all packed into an extremely compact form. Then, something extraordinary happened. This ultra-dense, superheated point began to expand. But it wasn't just any expansion. It was an expansion of such magnitude and speed that it's difficult for our human minds to truly grasp. In a fraction of a second, smaller than the blink of an eye, the singularity inflated. It expanded faster than the speed of light, spreading out the matter and energy it contained within. As it expanded, the singularity cooled. The energy it held began to transform, giving birth to the first particles of matter. It was from this inflation and cooling that the earliest elements were born: hydrogen, helium, and a small amount of lithium. These elements would later form the building blocks of stars, galaxies, and eventually everything we see around us in the universe today. This expansion, this cooling, and this formation of matter marked the beginning of time and space as we understand it. It was not just the birth of a universe, but the birth of our universe. It was a moment of creation, a moment of infinite possibility and endless potential. It was a moment that scientists, after years of study and observation, have come to call the Big Bang. This was the birth of our universe, a moment of creation that we now call the Big Bang. From that initial explosion, the universe began to expand and cool, forming the first particles and atoms. Picture this. In less than a second, the universe inflated from a singularity smaller than an atom to an astronomical size. This rapid expansion is known as cosmic inflation. As the universe cooled, it transitioned from a state of pure energy to a world of matter. During this phase, quarks, the smallest known particles, began to combine to form protons and neutrons. This is the era we call the quark epoch. As the universe continued to cool and expand, protons and neutrons began to bond, forming the first atomic nuclei in a process known as nucleosynthesis. This process created the first elements: hydrogen, helium, and traces of lithium. But the universe was not yet cool enough for these nuclei to capture electrons and form stable atoms. It was a sea of charged particles or plasma that scattered light in all directions, resulting in a universe that was opaque and dark. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei to form the first stable atoms. This event, known as recombination, allowed light to travel freely for the first time. The universe, once a foggy soup of plasma, was now transparent. The first light that was able to travel freely is what we now detect as the cosmic microwave background radiation. Fast forward a few hundred million years, gravity began to pull matter together to form the first stars and galaxies. The birth of these celestial bodies ushered in the epoch of reionization, marking the end of the universe's dark ages. This journey from a singular point to an expanding cosmos filled with galaxies, stars, and the diverse forms of matter we see today is truly mind-boggling. Every element, every particle, everything that makes up our world and us has its roots in those first moments of the universe's existence. Over billions of years, the universe evolved into the complex web of galaxies and stars that we see today. But how do we know all this? What evidence do we have that supports the Big Bang theory? Well, it's not as if we've stumbled upon some cosmic time machine to take us back 14 billion years. Instead, we rely on a trio of key pieces of evidence that tell a compelling story of our universe's fiery birth. First, let's talk about cosmic microwave background radiation. This is the afterglow of the Big Bang, the residual heat from that initial explosion that we can still detect today. It fills every corner of the universe and is remarkably uniform, just as we'd expect if the universe began as an extremely hot and dense point. Next, let's discuss the abundance of light elements. In the moments after the Big Bang, the universe was a hot soup of particles, with conditions just right for the formation of simple atomic nuclei. The theory predicts the ratios of hydrogen to helium and other light elements that we observe in the universe today, and guess what? The predicted ratios and the observed ratios align almost perfectly. Finally, we have the redshift of distant galaxies. As light from distant galaxies reaches us, it's stretched out or redshifted due to the expansion of the universe. This redshift is proportional to the galaxy's distance from us. The further away a galaxy is, the more its light is redshifted. This tells us that the universe is expanding in every direction, suggesting it all started from a singular point. These pieces of evidence are like breadcrumbs leading us back to the dawn of time. They build a consistent and robust narrative, one that withstands rigorous testing and questioning. Despite the mind-bending nature of the concept, the Big Bang theory stands tall in the face of scientific scrutiny, resting on a solid foundation of empirical evidence. These pieces of evidence all point towards the same conclusion. The universe began with a Big Bang. The Big Bang Theory is not just about understanding the past, but also about predicting the future of our universe. The significance of the Big Bang Theory extends far beyond a mere scientific explanation of the universe's inception. It's like a grand cosmic tapestry woven with threads of time and space and embroidered with galaxies, stars, and planets. And just like a tapestry, every thread we unravel leads to a deeper understanding of our place in this vast cosmos. The Big Bang Theory helps us grapple with some of the most profound questions about our existence. How did we come to be? What is our role in this vast cosmic theater? These are the questions that have haunted philosophers and scientists alike for generations. And while we may not have all the answers, the Big Bang Theory provides us with a framework to start piecing together the cosmic puzzle. But the Big Bang Theory isn't just a gateway to the past. It's also our crystal ball, peering into the future of our universe. Through the lens of this theory, we can predict how the universe will evolve, how galaxies will form and die, and even contemplate the ultimate fate of the cosmos. It's like a cosmic roadmap, charting the course of the universe from the microseconds after the Big Bang to billions of years into the future. The Big Bang Theory also underscores our interconnectedness with the universe. Every atom in our bodies was once a part of a star that exploded in a supernova, spewing out elements that eventually coalesced to form our planet. We are, in the most literal sense, stardust. The Big Bang Theory, then, is more than just a scientific theory. It's a testament to our curiosity, our quest for understanding, and our insatiable desire to uncover the mysteries of the universe. It's a reminder that we are not mere spectators in this cosmic dance, but active participants, each playing our part in the grand cosmic narrative. So the next time you gaze up at the night sky, remember, you're not just looking at stars, you're looking at the history of everything,